Okay, let's start our last section in Chapter 4. This is on another application of integration, another application of derivatives called differentials. Okay, so the idea here is that we are going to use a line to approximate something from a curve. This might seem a little bit useless when you're given functions, but when you are given a function, it's easier to sort of see what's going on and wrap your head around the idea. And then later, if you just had a table of values, just a picture, but you weren't told the function, the idea would still remain and you would be able to do some approximating. There's also some application problems at the end, and we will do one of those, where in the end what we're trying to do also is approximate an amount of an error. Okay, so actually, here we go. So we are trying to estimate amounts of error. We're going to use differentials, which actually is going to concentrate on, sort of the slope of this tangent line here. And let me use this picture to explain it. There's a lot of stuff all over here. There's c, f of c. Let's maybe start there because that might be the easiest thing. So here's a function f. On this function f, we're looking at an x value called c. So if this is an x value called c, then this point would be c f of c. That's my xy. All right. Now I want to go back to like when we were finding derivatives using a limit definition. Instead of labeling this x value as a different letter like d, we're going to label the distance between the two as delta x. So in these approximations, delta x will be really small, but to see what's going on in the picture, we have to make delta x a little bit bigger so we can see it. So delta x is the distance between this point and this point, so this x value is c plus delta x. I said the word point, but I should have reserved point for here. So this point is on a line. So we're going to start talking about, the slope of the line when we start referring to this point. But if we go up here onto the curve, if this was c plus delta x, then on the curve, which is given by the function f, this point is c plus delta x, f of c plus delta x. We are going to call this distance from this y value to this y value. See this? This is delta y. Okay, so that's important, so I'm going to circle that. That's delta y. Okay, now what is dy? dy isn't clearly illustrated on this picture right now, but what dy is going to be is this distance. And we'll get into how the derivative is going to come into play here. But this distance is going to be dy. And you see how similar that the length of that line is to the length of this line, right? That's the difference in these y values. So you're again trying to look at the difference between y values on a curve, and to find that, you're looking at the distance between y values on a line. All right, so where does this word differential come in, and what is a differential? Well, you know that if we had a function, if we had some function y equals a function of x, then for its derivative we could write dy dx. Now we could write y prime, but I'm going to choose to use the Leibniz notation here. dy dx equals f prime of x. We'll just take this expression, dy dx equals f prime of x, and multiply both sides by dx. Multiply both sides by dx. What would you get? You get this right here. So this is just taking a derivative. But when we have y on this side, we're going to say that the derivative of y is dy. And then on this side, to take the derivative, it's almost like a chain rule. With implicit differentiation, we're going to say the derivative of f of x is f prime of x times whatever differential we need to represent this letter. Or again, just think of it as saying dy dx equals f prime of x, and then multiplying both sides by dx. All right, graphically, I want to get into the graphical description of what we're doing. And I'm going to be exaggerating a few things because if you could tell, 1.9 is pretty darn close to 0.2. So I'm going to pretend it's a little bit farther back. 2.04 is really, really close to 2, and we won't be able to see anything there. So I'm going to sort of exaggerate where those points would be. But we're trying to use differentials and the graph to approximate these things, the actual values. I just want to show you what the heck it means. What is approximating f of 1.9 using differentials? What is that going to do for you? Well, 1.9 is somewhere to the left of 2. So if I kind of back up to some place where I could see the difference, I have a y value on the line. I also have a y value on the curve. So actually, this is going more towards the idea of a linear approximation here. What they're saying is we could use f of, now this is actually even, I'm all the way back here at 1. I could use f of 1, which let me show you about where that is, to approximate, I'm sorry, I can use the value of the tangent line at 1 to approximate the value of the curve at 1. All right, so let's not move so far away. Let's go to some place that, exactly where they want us. They want us at 1.9. So try to find the y value for the tangent line at 1.9, and that's supposed to approximate the y value for the curve at 1.9. You see how close they are? So the closer we get, I mean, you can see how far apart these values are as opposed to how far apart these values are. If you're trying to approximate a y value for a curve, you can use the y value for the line. Now, again, that idea is called a linear approximation. And again, I'm telling you this because I know a lot of you will want to go, find some supplemental things or at least read about this stuff in your book. Maybe go to your study plan and WebAssign. So if you look for linear approximation, that focuses more on this idea of just using a y value of a tangent line. Again, let's jump over to this one. A y value of a tangent line, certain spot on the tangent line, that's maybe for this x value here, to approximate the y value for the curve. You could see these are pretty close together. Okay, same x value, different y values, but they're close. And you can use this y to approximate that y. Okay, what will you have to do? What will you have to demonstrate knowledge of, in WebAssign and a quiz, whatever? I will want you to be able to evaluate and compare, but evaluating will allow you to compare them. Evaluate dy and delta y. Now we're actually going to find dy first, and I actually also do want to do both of these problems. I usually save you the odds, but this is a good one to help you understand what we're finding. We're also going to draw a picture, but first let's just do the math here. All right, how do we find dy? dy is really easy, guys. Very, very, very easy. Okay, so we have, for number 7, y equals x cubed. So to get the differential, we just take the derivative, which is, good, I hope you all said 3x squared. Now don't forget the dx, because we're using differentials. Now what they're giving us here to plug in is that x is 1, and delta x, which is dx, is 0.1. Now, I feel like I didn't really explain delta x or dx much. I was talking about delta y and dy. So let me hop off of doing the actual math here to show you what we're finding. You know what the graph of x cubed looks like. There's our graph of x cubed. Okay, so if I am interested in the point where x equals 1, let's put that maybe right here. And I want to use dy to approximate delta y. Well, dy comes from the fact that we are looking at dy dx. dy dx is the slope of a tangent line. So I'm going to draw a tangent line here. All right, after drawing that tangent line, know that what we are doing is, say for if the distance between 1 and the next value we're looking at is delta x is sorry, that's not 0.01, it's 0.1, is 0.1, then, and clearly I have to make that bigger than what it really would be to scale, just so that you could see the difference. So 0.1 is the change in x, and I'll leave it delta x right now. So we're interested in this y value. And actually what we're interested in is the change in y's from 1 to 0.1. Okay? The change in y's. Where was this y value? Where was this y value on the curve? How are we going to approximate that? Well, we're going to look at the change in these y values from the tangent line. Where was this y versus where was this y? This distance right here is called dy. This distance here is called delta y. But please, please, please notice that no matter which distance you're talking about, I have this distance between here and here, whether I'm on the tangent line or I'm on the curve. These two distances are the same thing. So that's why it says delta x equals dx equals 0.1. Again, this one is referring to the curve, this one is referring to the line. But those distances are the same whether you're looking at the curve or the line. If you need to go back and play that 8 more times, that's fine. If you need to go to YouTube and hear somebody else say it, that's fine. But I just wanted you to get the general idea of what delta x versus dx is, but they are always the same. All right, here comes the easy part, guys. You just plug that stuff in. dy is 3 times x squared times dx. And that's 3 times 1 times 0.1, which gives you 0.3. So this value right here is 0.3. That's going to approximate this value. Now you could see this one looks a little bit bigger, right? So let me show you how to get delta y, and hopefully we'll notice that it's a little bit bigger. All right, delta y is going to be what the y value was or is up here minus what the y value is over here. So how do I find this y value? Well, I plug in 1.1 to the function. Why? Because this is 1, this is 1, plus my change in x of 0.1. So this x value is 1.1. So I want the y value at the x value of 1.1. Then I want the y value at my starting point. I want the y value here. Now this is, I'm using the same notation as I would if it were a function, right? F of 1.1 minus f of 1. All right, so how do we find this? Well, we go to the original function and we say that's 1.1 cubed, that's 1 cubed, so this is 1.331. You could check that on your calculator. Minus 1, this should look a little bit like Pascal's triangle, which is kind of cool. And that's 0.331. So, do we see what we saw in the picture? I believe we do. This value is smaller than this value. Your dy was a very good approximation for delta y, but it was smaller. And you could see that from the picture. All right, and because this is a video, you can go back and replay that and try to make it make some more sense. All right, so what I want to do now is number 8. Okay, for number 8, just a different function. And again, if you want to quickly think about, 6 plus 2 or minus 2x squared, that's going to be a upside down parabola. And we'll think a little bit more about what where this crosses the x-axis. You'll see why I'm putting those values there in a second. All right. But we are, again, going to be looking at now x equals -2, and at x equals -2, we're going to want to use an amount of error in these y values to, we're going to use differentials to approximate that. So again, we're going to find dy first, because that's our easier one, and then we'll find delta y. All right, so how do we start? To get dy, we want to use the derivative. dy equals the derivative of 6 minus 2x squared, and we have a dx. All right, now I'm going to plug everything in, my x value and my change in x. Now again, if my change in x is 0.1, positive 0.1 from negative 0.2, we're actually thinking about another x value right over here. Alright, so this is going to give me -4 times x times dx, which is going to be 8 times 0.1, that's positive 8, so that's 0.8. Alright, that was dy. We're going to use dy to approximate delta y. Delta y, again, I don't want to talk about the picture too much because I just want you to see basically how simple the math part is. Delta y is going to be y evaluated at my new x value. Now -2 plus my change in x is going to be -1.9 minus the y at my original y value, or my original x value. Okay. So, if I'm plugging in a -1.9, I'm getting 3 points. Well, let me do a little bit of work, a little bit of this out for you. So this would be 6 minus 2. Make that look a little neater. 6 minus 2 times -1.9 squared minus 6 minus 2 times -2 squared. Alright, so this is 3.61, positive 3.61 multiplied by -2, so this is 6 minus 7.22. This is 6 minus 8. So that's -1.22 minus -2, which gives me 0.78. And what you want to notice in the end numerically is that these two are very similar. Okay, very similar. Why now is my dy a little larger than my delta y? So I want to try to get you to understand by looking at the picture. Let me extend this out a little bit farther. And by the way, you can get the x-intercepts if you take this and set it equal to 0. You would get 6 equals 2x squared, or 3 equals x squared, or x equals plus or minus the square root of 3. So this is plus or minus about 1.7. Alright, so I just want to be drawing these tangent lines at this tangent line at the right spot. So I will have a tangent line here at -2, and if I could just kind of magnify what I did and sort of exaggerate the curve a little bit. So pretend I'm zooming in on this part, and I have a tangent line here. This might be a little bit easier to see. What I did was I used this for my dy. This goes from -2 to -1.9 to approximate the difference on my curve. So here now for my curve, this distance here is delta y. So my dy is going to be a little bit larger in this case than my delta y. Okay, pause this if you need to try to understand that picture. And the last type of problem that we need to do is one where it's an actual application problem. So this is talking about a spherical balloon. So let me draw a picture, and you don't need a picture, but you have a spherical balloon, you have a radius, and they're telling you that the radius of this balloon is supposed to be 8 inches. However, there's a possible error in your measurement. So we're going to call that dr, because delta r, which would be equal to dr, is about how far over. We're going to say our r value is off, right? There's a little bit of an error maybe in our radius. So that is, and I'll put a plus or minus because we could be off by too high an amount or too low of an amount. Okay. So let's come up with an equation to use differentials to approximate the possible propagated error, that's just going to be the amount of error, and computing the volume of a sphere. So we have the volume of a sphere, which I would give to you, or you could Google the formula. So if we want to introduce differentials now, we're going to take the derivative of v, or dv dr, and multiply both sides by dr. The derivative of this side, when I bring down the 3, it's going to cancel with the denominator. So 4 pi r squared. Don't forget your dr goes over here. Now let's plug in the values. So that's 4 pi times 64 square inches, right, when you square your radius, times plus or minus 0.02 inches. And you can do the math. That should work out to be 5.12 pi. And you can even see the units work out. Inches squared times inches is inches cubed. So that is the amount of propagated error for the volume. So you've done part A. We're going to get to percent error in a little bit, but let me go to the next page first to tackle the surface area. Alright, so we just need a surface area formula. It happens to be the same as the derivative of volume. Alright, now let's use differentials. So take the derivative of this side, but don't forget your dr. Put in the same given information as before. So this was what, 8 inches. This was plus or minus 0.02 inches. And when you do this math, you get 1.28 pi, and that's inches squared. Now, again, I don't know if I pointed it out on the last one, but it should make sense. We're talking about surface area, so we came up with inches squared. When we were talking about volume, we ended up with inches cubed. So I can get an approximation. Like this is about 16.08 cubic inches. The reason I left it with the pi in it is because of this part C that we're going to do now. When you want a percent error, you basically want to know how big of a deal is this. Is approximately 16 cubic inches, is that a big deal or not? What is the volume of the sphere supposed to be? Alright, well the volume of the sphere is supposed to be 4/3 pi times 8 inches cubed. I'm just using the original formula up here. You can work this out and you will get 2048 thirds pi, and again that's cubic inches. So comparing what our error is to what the actual value should be is the same as the proportion dv over v. This is called, and this is important, you want to get this in your notes, this is the relative error. And we're going to get find the relative error to get our percent error. It's just a matter of moving a decimal or multiplying by 100. So I'm going to leave this in terms of pi because then we won't have to approximate our answer so much. These are both cubic inches, I just want you to realize. So the cubic inches will cancel, the pi's will cancel, and now you just have to take 5.12 divided by 2048 thirds, and you get 0.0075. That is called your relative error. So how do we turn that into a percent error? Just multiply by 100. So that is a 0.75% or 0.75% error. Okay, so 16 cubic inches might sound like kind of a lot, but it's less than a 1% error. That being off by this much in measuring your radius causes you to be off by this much in your volume. So you can finish that with the surface area. Try it, maybe pause the video and try to find the percent error for surface area, and then come back and see if you got that right. Okay, so hopefully you found your 256 pi by putting your 8 inches into this formula. Then we are getting the proportion of the amount of error over what the surface area should be. You get 0.005. This is called your relative error. And as a percent error, you multiply by 100 and get 0.5%, or a 0.5% error. So if you are off by this much in measuring your radius, you're off by as much as 0.5% in the measurement of your surface area. And that is what we use differentials for. Okay, so if you have any questions on the WebAssigns, again, do your ask your instructor or send me an email. Good luck.